0.1. Then making R the subject of the formula, we now have 0.1 all over 0.05, which will now give us 2 ohms. From our equation 1, capital E, the electromotive force, minus 0.3R is equal to 0.9. Since R, we have gotten our R to be 2 ohms, we now substitute the value to have capital E minus 0.6 equals to 0.9. From capital E minus 0.3 times 2 equals to 0.9. Then for the resistance, R1 is equals to capital V1 over I1, which is equals to 0.9 over 0.3, which will give us 3 ohms. R2 is equals to capital V2 over I2, which is equals to 1.0 over 0.25, which will give us 4 ohms. Electrical energy and power. Electrical energy. The work done, capital W, or energy released in 1 joule when 1 coulomb moves between a potential difference of 1 volt. Energy is equal to capital W equals to Q, capital Q times capital V joules, which is also equal to capital IVT joules, which is equal to capital V squared T all over R squared, or which is equal to I squared R T joules. Example 1. A heater coil is required to give 420 joules every 7 minutes when working for a 2 volt supply. When the length of 32 SWG Eureka wire is required to make the coil, if the wire has a resistance of 0.8 ohms per minute. Solution. Let capital R be resistance of the heater coil. Heat to be generated by the heater coil, capital V squared T all over R is equals to 2 squared times 7 times 60 to convert 7 minutes to seconds all over R. But the energy is 420, which is equals to 2 squared times 7 times 60 all over R, making R the subject of the formula. We now have R, capital R, is equals to 2 squared times 7 times 60 all over 420. Length of Eureka wire required is equals to 4 over 8, which is equals to 0.5 meters. Example 2. A potential difference of 6 volts is used to produce a current of 5 amp for 200 seconds through a heating coil. Calculate the heat produced. Solution. Heat produced is equals to IVT, which is equals to 5 times 6 times 200 joules, which will give us 6,000 joules. Example 3. Looking at figure 4.7 example, calculate the total heat energy developed in 5 minutes by the system above. Solution. The effective resistance capital R is parallel is given by 1 over capital R is equals to 1 over 40 plus 1 over 40, which is equals to 1 plus 1 all over 40 to give us 2 over 40. Therefore, capital R is equals to 40 over 2, which is equals to 20 ohms. The total energy developed is equals to I squared RT, which is equals to 1.2 squared times 20 times 5 times 60, which will give us 8,640 joules. Electrical power. Electrical power, capital P, is defined as the energy liberated per seconds in a device. From the above definition, we can express power in any of these 3 forms. Capital P is equals to VI, which is equals to V squared over R, which is equals to I squared capital R, which is in watts. The unit of electric power is watt, capital W. The larger unit is the kilowatt, kW. 1 kilowatt equals to 10 raised to power 3 watts. Example 4. Looking at figure 4.18, calculate the total power drawn from the cell in the circuit diagram above. Solution. Combine resistance in parallel. Capital R is equals to 4 times 4 all over 4 plus 4, which gives us 16 over 8, which is 2 ohms. Combine resistance in parallel is equals to capital R equals to 4 plus 2, which gives us 6 ohms. Therefore, the total power drawn from the cell is equal to V squared over R, which equals to 12 squared over 6, which equals to 144 over 6, which equals to 24 watts. Example 5. Looking at figure 4.19 diagram example. In figure 4.19, current I passes through parallel combination. If the power dissipated in the 5 ohm resistor is 40 watts, calculate the power dissipated in 10 ohm resistors. Solution. The potential difference across the two resistors in parallel is the same. P power is equals to V squared over R. 40 is equals to V squared over 5. V squared, making V squared the subject of the formula, we have V squared equals to 40 times 5, which will give us 200. V is equals to the square root of 200, which is V. Therefore, the power dissipated in the 10 ohm resistor is equal to V squared over R, which is equals to V, which is equals to 200 squared over 10, which gives us 220 watts. Buying of electric energy. Commercial power is consumed in kilowatt hour, kWh. The electrical energy consumption in kilowatt hour is measured with electric meter. From the meter reading, the electrical energy consumption can be calculated. In Nigeria, most of the electrical energy supply is produced at the Kainji Dam. It is then distributed and sold in kilowatt hour units by the Power Holding Company of Nigeria. 1 kilowatt hour is the quantity of energy supplied by working at the rate of 1000 watt per hour. 1 kilowatt hour is equal to 1000 watt hour for 1 hour. 1 kilowatt hour is equal to 1000 times 60 times 60, which is equal to 36 times 10 raised to power 6 joule, or 3.6 megajoule. Example 6. Calculate the power consumed by an electrical device of resistance 40 ohms connected to a 240 volt main supply. What will be the total cost of using this device throughout a month of 30 days at a cost of 5 kobo per electrical energy unit? Solution. Power consumed is equal to V squared over R, which is, by substituting the values, we have 240 squared over 40. Energy consumed in 30 days is equal to V squared T over R, which is equal to 240 squared times 30 times 24 all over 40 times 1000. Cost at 55 kobo per kilowatt hour. We now have 240 squared times 30 times 24 all over 40 times 1000 times 5, which gives us 55,184 kobo per kilowatt hour of 51 naira 84 kobo per kilowatt hour.